for stochastic evolution equations in M-type 2 Banach spaces.
Okay, thank you. And first, I would like to thank Didro for his invitation, and also all the organizers for this wonderful SPDE program, and also for the Newton Institute for financial support. It's my pleasure to give a talk about the invariant measure for stochastic evolution equation in M-type 2 Banach space. This is based on the joint work with Didro and Isabel Zimmer. Okay. The paper to appear in this general stochastic evolution equation. Okay. So this is the outline of my talk. So in the first part, I'll just give a brief formulation for our research problem. Basically, I'm interested in the studying the existence and uniqueness of invariant measure for stochastic evolution equation in M-type 2 Banach space. And then I also give some historical comment about some existing result in this direction. Okay. Then the second part, I will briefly discuss the structure of the underlying Banach space and some other basic assumptions. In the third part, I will discuss our main result on invariant measure for stochastic evolution equation with the Lipschitz and the dispersibility condition. Then the last part, I will discuss how to extend our result from the Lipschitz condition to the local Lipschitz condition. Okay. So here we consider the following stochastic evolution equation on an M-type 2 Banach space E. Then this is our equation. Then A is just the generate for some strongly continuous semigroup on this Banach space. Then F is some measurable function from the Banach space E to E itself. Then sigma is a measurable mapping from E to some so-called Rodney operate space, we denote by RHE. So the definition will be discussed in the second part. Then W is just a cylindrical Wiener process on some separable Hilbert space H. So to study this type of stochastic equation, we need the theory of stochastic integral on the Banach space. So this is the M-type 2 Banach space, which was developed by Ned Hart in 1978, and also a few years later, Ned Wheeler 1982 independently. Okay. In fact, this is his thesis. I think it didn't publish and never published. For the existence and uniqueness of the minor solution to the stochastic evolution equation on M-type 2 Banach space have been studied by Brzeziak and his corporate in the past 15 years, and also by Underjat in 2004 in his thesis, I think. And also for the martingale solution, this is just like the weak minor solution. And then the invariant measure for stochastic evolution equation on M-type 2 Banach space was discussed in this paper by Brzeziak and Katerick in the 1999 paper. But in this paper, they have a very strong condition about the semigroup. Basically, they assume that the semigroup generated by the operator A, which is compact. Okay. So of course, this is a very restrictive condition. But in our work, we try to establish the existence and uniqueness of the invariant measure by introducing some dispersibility condition and try to get rid of this compactness condition. Okay. So here are some historical comment about the stochastic evolution equation in the Hilbert space case. Okay. I just mentioned, so this is a very famous classical book in this area for the stochastic evolution equation in Hilbert space. I think this book by Dapprato and Dvorak already like cited by people like 1,700 times. In this paper by Maslovsky and Sandler in 1998, this is a quite good survey paper. Okay, they review all this existing result by that year about the uniqueness and the stability of the invariant measure for SEE in hyperspace. So to consider the existence of invariant measure for stochastic evolution equation in hyperspace, so the main criteria, this is the so-called Kolmogorov-Bogoliubov criteria. Basically try to establish the tightness of a sequence of probability measure related to the semigroup. Then also, in this paper by D'Aparato, Gaterick, and Zabatic in 1992, they introduced the so-called compactness method and the dispertivity method to prove the existence. Okay. Then recently, in this paper by Sahari and Stannard, they also use this Korolov-Bogoliubov criteria to establish the existence for invariant measure, but they consume some like local Lipschitz condition. But of course, in the previous paper, mainly use Lipschitz condition. Okay. So there are three basic methods to prove the uniqueness for the invariant measure. So the first one is try to verify the so-called strong wave failure property and then the reducibility property for the semigroup associated with the solution of the stochastic evolution equation. So this is considered by many authors in this for this method. So usually for this method, you have to require some boundariness for the coefficient, like the drift coefficient. So the second method is the Lyapunov method. So this method was used by Ichikawa, Maslovsky, and also later Leharita. They basically introduce some Lyapunov function in this in the hyperspace. Then the third method is the dispersive method introduced by D'Aparato, Gaterick, Zabatic in the 1992 paper. I think these two methods are kind of similar because they try to use all this either the Lyapunov function or the dispersive condition to establish the some a priori estimate for the moment of the solution. Then from there to get the uniqueness of the invariant measure. Okay. So just briefly review all this method. Of course, then in this paper we try adopt this dispersive method. Okay. So now in this part, I try to briefly discuss the structure of a Banach space. So we assume that we have H and E, so they are separate Hilbert space and the Banach space. Then E, K from 1 to infinity is just some fixed orthonormal basis in this Hilbert space H. Then we need to just a definition for this the gamma ordinary from operate from H to E. So let gamma to be a canonical cylindrical Gaussian distribution on H. Then we say this operate L is a gamma non-referent if the image measure of gamma induced by L has extension to the sigma additive measure gamma L on the Banach space. Okay. Then we can introduce this norm in this space RHE, so that this RHE, this space becomes to be a separable Banach space under this measure, under this norm. Okay. So this was proved by Leonhard in his thesis in 1978. Then for this gamma non-referent operator, then we can define some trace operator. So if we have a binary boundary map G is from this product space to the real value space, then we say this trace operator is given by this integral with respect to the this measure gamma L on this Banach space, then we can easily show that this trace operator can be expressed by using the orthonormal basis of the Hilbert space H. Okay, this one. Of course, we can easily see that if this E becomes another separable Hilbert space, then this just the the common ordinary operator just the Hilbert-Schmidt operator. Okay, so this is well defined. Okay, so this is finite also by using the Fernic theorem. So this is just some basic definition about the some dual mapping in the Hilbert space. Okay. So of course, in general speaking, this is a multivariate mapping. But if the norm of this Banach space is Gaussian differentiable, then this Jx becomes a single value mapping. Okay. So this is just the definition for this semi-inner product space. So this mapping from this product space to either to the complex or the real value space satisfies the following four conditions. Then we say this space, vector space E is called the semi-inner product space. Then this bracket is the semi-inner product on this space V. Then by using the the Banach theorem, we can easily show that any Banach space can be made into a semi-inner product space. Okay. And also now we introduce an important type of Banach space, so which we'll be using in this talk. We say a Banach space E is of M type 2 if for any E-value martingale MN, the following inequality hold. Okay. So this constant L is of course only dependent on the structure of the Banach space, does not depend on N. So if this inequality hold, then we say it's a M type 2 Banach space. Okay. Of course, you can change it 2 to be any real number p larger than 1, they get some kind of M type P space. But in our work, we only use M type 2 Banach space. Okay. But this property is crucial for us to, for example, you need to have some kind of double inequality on the Banach space. Okay. And also this just M type 2 Banach space is not enough because we need to have some kind of smooth structure of the Banach space. So we introduced the following assumptions. We assume that there exists some real number p which is larger than 1 and some constant kp positive such that this function, the norm x to the power 2p, so which is twice French differentiable on this Banach space, and satisfy this the second derivative dominated by the right hand side. Okay. So they just give some example what kind of space satisfy this condition. Okay. So basically all this Hilbert space, of course, and then the LR space for r larger than equal to 2 satisfy this condition. Okay. Of course, this assumption is still quite restrictive because we needed to use this condition to get us the priori estimate for the solution. Okay. And also in my early paper, we proved that if the Banach space satisfies these assumptions, then this Banach must be can become to be M type 2 Banach space. Okay. So the next assumptions, these just are the basic assumptions about the driven noise for our stochastic evolution equation on the Banach space. So basically, we assume that W is a H cylindrical Wiener process depending on this probability space. Then we say WT is a boundary linear operator from H into this L2 space such that the following two properties are satisfied. Okay, so just some basic property for the winner process. Okay. So this just gives some preliminary result about the Banach space structure and then the driven noise. Okay. Now in this part, I will discuss our main result on the existence and uniqueness of invariant measure for the stochastic evolution equation on Banach space with the Lipschitz and the dispatchability condition. Okay. Of course, we have some basic like standard assumptions about the semigroup and the condition for all these coefficients. So we assume that A is the generate for some strongly continuous semigroup on the Banach space. Then both F and the sigma of this coefficient satisfy the Lipschitz condition. So this is standard condition. And also we define this space of stochastic process. Basically, this is some kind of like an adaptive process, such that this integral is finite, almost surely. Okay. So now we can define the this the minor solution to our stochastic evolution equation on the Banach space E. So if X belongs to this space n square E, then satisfy the following integral equation. Okay. So just our definition for the minor solution. So this is parallel to the Hilbert space case. Then of course, under the standard Lipschitz condition, we can easily show that there exists a unique minor solution to the stochastic evolution equation. And also the solution has a continuous modification. So this is somehow standard result. Now the main result of this talk is the following theorem. Okay. We assume that this E, the Banach space, the norm satisfy the our assumptions discussed earlier, and then we have this this unique semi-inner product on this product space. Then we assume that all these A, F, and sigma satisfy the our standard assumptions. In addition, we have to introduce the dispatchability condition given by this inequality. Okay. So in this condition, here An is the Yosida approximation of the generator A. Then this bracket is just the semi-inner product on the Banach space. Then Kp is the constant from the assumptions about the smoothness of the norm. Okay. Then omega is a positive constant. Okay. So this is somehow the dispatchability condition. So we require this to be true for n large enough. Okay, n large enough. So then, based on the our Lipschitz condition plus this dispatchability condition, we can show that there exists exactly one invariant measure for our stochastic evolution equation, and also this invariant measure is strong mixing and satisfy this weak convergency, and then we can get the rate of convergency also, which is somehow exponential convergent convergency. Okay. So this is our main result. So here just briefly sketch the proof idea for our main result. Okay. So here we adopted the remote start method introduced by D'Apparato, Katerick, Jabratic in their 1992 paper. Of course, this is also discussed in this classic book by D'Apparato and Jabratic. So the idea is we try to introduce another winner process which is independent from the previous one. Then we can define this winner process on the whole, like the real space. Okay. So the time t now is on the to be any real number. Okay. you can consider the following the so-called regularized equation, which is driven by this now this extended Wiener process on the whole real line. Okay, the time. Yeah, please.
What is V? Is it W?
Where?
The definition of W1.
V is another Wiener process.
Another customer.
With another Wiener process with independent of W. Okay, so we can use V and W to construct this W1T Wiener process. Then we consider the regularized equation, which is driven by this W1 Wiener process. And also we replace A by the Yoshida approximation. So basically this is some kind of approximating stochastic differential equation. Of course, then we can talk about the strong solution for this equation. Okay. So this regularized equation has a strong solution under our condition. So this was already established by Brezhnev and Elvers in 2002, and also by Infra in this thesis by Neilhart in 1978. And then based on the Lipschitz condition, we can first show that we have this convergence in the LQ sense. So this x, xt is denoted by xt sx. So this becomes the solution of the following equation. So now, of course, this equation is also driven by this new or the extended Wiener process on the whole real line. Of course, we say this is a minor solution, basically, a minor solution, because this is we have this operator A here. Okay. Then we have the two main steps to prove the existence and uniqueness of the invariant measure. So the first step, we need to establish a priori estimate for some moment of the solution to the stochastic evolution equation. So the idea is we just try to apply the Eaton formula to this process, which is the solution, strong solution of the regularized equation, to this function. Okay, this function is already given the assumptions for the smooth structure of the Banach space. Then we take the expectation, we can get the following equation. Okay. Of course, in this equation, for this integral, this bracket is for the same inner product, okay, on the product of Banach space. Then we use our assumption 2.2 basically about the smoothness of the norm, and then use our disparative condition, and use some this is Young inequality. We can get the following estimate. It's just some technical stuff. Then of course we can apply Galois inequality to get some estimate for this moment. So we get this estimate. Then we just let n go to infinity because we already have the convergence of the strong solution to the minor solution. Then we get this nice prior estimate for the solution of the moment of the solution. So this is the first step. We try to get this kind of a prior estimate for the moment. Now in this second step, we try to get some kind of like Cauchy sequence in some L2 space. Okay. So we consider this the difference between the two solutions. They start with a different time. Okay, one start with the negative data, one start with negative data. Okay. Then we apply Eaton formula, and then the procedure is the same as before. Of course, when you apply Eaton formula, we can only apply to the approximation process xn basically. Okay. They use the similar technique, we can get this estimate. Okay, this estimate. Then we can now let t equal 0. We get the estimation for the difference of the two solutions started with a different time. One is negative number, one is negative data to the second moment. We get this estimate. So this means that we have this sequence of non-variable, which is a Cauchy sequence in this L2 space. So this is how they should converge to some non-variable also in the same space. So then we can claim that, so basically the law of this non-variable eta, which is will be the unique invariant measure, satisfy all these required condition specified in the theorem. Okay. So first we can notice that this probability measure, which is the law of the solution xt0x, which is equivalent to this one, will converge to the law of eta, which is derived by mu weakly. So this by the Cauchy property. But then this is equivalent to say this measure pt star. This is the dual semigroup applied to the Dirac measure will converge to mu weakly. Okay, with this weak convergency. Then from this weak convergency, we can prove the basically we get the mu should be an invariant measure for the same group. Okay. So these are some standard derivation for this invariant measure property for mu. Okay. So this is about the existence of the invariant measure. Okay. Then we need to establish the uniqueness also. So the strong mixing properties by using some standard result from this book by the brother Magic. And also the weak convergence of the PT star delta x convergent mu, which is somehow equivalent to this convergency. So now based on the previous convergence, we can easily prove that this is by some dominant convergence result. We get this phi pt star nu. This will converge to phi mu. Okay. So this means that, so basically the dual semigroup pt star acting on this any probability measure on the Banach space will converge to mu weakly. We get this result. And also from this result, we will get the uniqueness of the invariant measure. Okay. So this is quite a simple argument. We get the uniqueness based on this weak convergence. Okay. And also we can use the primary estimate for the second moment of the solution. We can integrate the this rate of convergency. Okay. So this just sketch the proof idea for our main result under the Lipschitz condition and the specific condition. Okay. So the following remark just try to find some sufficient condition to guarantee the our dispensability condition imposed in the main result. Okay. We assume that if we are this A is generated for some, for example, strongly continuous semigroup. Okay. Omega can be any real number. Then we can use the here you see the theorem to prove that this A and X, this is the same unit product, will be dominated by the right hand side. Okay. So for n larger than omega 1. So if the diffusion coefficient f plus the diffusion coefficient they satisfy this condition, then we can easily see that then the dispensability condition hold for any omega belong to this interval. Okay, this interval. When n is large enough, basically n larger than equal to this number is enough to guarantee the dispensability condition. Okay. So it just give you some sufficient condition for the dispensability. So now we discuss one example, how we can apply our result to some SPDE. Okay, we assume that AP is the operator defined by the following expression. So this is just a second order differential operator on the real line. Okay. Then this is just our LP space intersection with some subgraph space. So this is our generated AP. P should be largely equal to 2 in this case. So then we assume that all these coefficients for the operator A, B, and C are given by this specific format. Of course, all these just some A to B0, B1, C0, just some real number. We assume they will satisfy some condition. Okay. So to get this differential function, differential coefficient f, we first introduce this function psi, which is a decreasing function, satisfies some Lipschitz condition. Then we also assume that this Lipschitz constant is denoted by this number, which are related to all the coefficient for the operator AP. Okay. Then we can define f to be the Lipschitz operator associated with this function psi in this way. Okay. Of course, use this definition, we can easily show that f, this mapping is Lipschitz. Okay, this is Lipschitz mapping. So now we introduce our diffusion coefficient. So in this example, we just introduce a constant diffusion coefficient. Okay. We assume that kappa, which is in this LP space from the real number, real line to the Hilbert space, for p larger than or equal to 2, then H is any element in the Hilbert space. Then we can define this operator sigma by using this expression, this inner product. Then basically in this paper by Brezhnev and Pejat in 1997, they proved that this sigma indeed is a gamma-logarithmic operator. Okay. So now we can consider the following stochastic evolution equation on this Banach space. E is just a LP on the real line. P is any number larger than or equal to 2. So we already introduced all this, the operator, the coefficient, f, and the sigma. Okay. Of course, we have to verify to see if all this, the operator and then the coefficient satisfy our condition or not. Yep. So after some basic calculation, we can show that if p equal to 2, then A2 plus f, which is not a dissipative. Okay, it's not dissipative in the L2 space. However, if we can choose some p large enough such that this is true, then this operator AP minus C02, this becomes a dissipative operator in this Banach space, LPR. Okay. So this is in the, by using the theorem in the book by Fortunini.
The notation A2 and AP just refers to the space?
Just the space, yeah. If P equal to 2 is in the Hilbert space, L2. If P is larger than 2 is in the Banach space. Yeah. Because here we try to compare the Hilbert space L2 and the LP's case. Yeah. So basically, if we consider the A2 operator, which is not plus the F is not dissipative in the L2 space. But if we consider AP operator, if the P is large enough, then this if the AP becomes to be dissipative, then we can verify AP plus F is also dissipative. Yeah. So this is required in for our condition. So just a basic calculation for this differential coefficient of f. Then we denote by k times this norm in this Banach space. They combine all these previous results. We can easily see that this same inner product between AP, XX, and FXX. Now this becomes to be somehow is dissipative if this number C02 plus K, which is negative. Okay. So this is true if we can basically find some all these number satisfy this equation. Okay. So therefore, all these assumptions in our main result are satisfied for this example. Okay. So we can apply our result to this special case, to the example. And also for the non-compactness, we try to relax our condition about the semigroup generated by operator A. So in the paper by Brezhnev and Gadrick, I think they have the compactness assumptions for the semigroup generated by A. So here we try to find our example, show that the semigroup generated by our AP is not compact. In fact, here we only partially successful because we can only prove that A2 is not the semigroup generated by A2 is not compact, but we have not yet proved directly the semigroup generated by AP is not compact. But we believe that this is true. Okay, we believe that this is true. I don't know. Maybe there's some expert in this area that know the compactness of the semigroup generated by AP. Okay. So hopefully we can prove this somehow like the conjecture soon. Okay. So basically, this example showed above cannot be covered by any assumptions in all these previous paper. Okay. So now this is the last part of my talk. So we'll briefly discuss how to extend the result from the Lipschitz case to the non-Lipschitz case, log-Lipschitz case. So these are some standard assumptions about the same group generated by the operator A. So this is just bounded. So you have the constant m, then times e to the power beta t. Okay. So all these basic assumptions about the our Banach space is the same. Okay, still satisfy the smoothness of the norm given by this assumption 2.2. Then we still have this same inner product on this product space. Now we relax the condition from Lipschitz to log Lipschitz condition. Okay. So basically, assume that f and the sigma satisfy the log Lipschitz condition given by these two inequality. Okay. So in addition to this local Lipschitz condition, we also assume some kind of like either linear or quasi-linear growth condition for the drift coefficient and the diffusion. Of course, for diffusion, this is linear, but then for the drift one, not as linear. Okay. Fx may have some polynomial growth. Okay. So under the local Lipschitz condition plus this kind of quasi-linear growth condition, we can prove that the solution to the stochastic evolution question has a unique global multi-solution. Okay. So basically, these two conditions guarantee the solution does not explode, because otherwise your log solution not enough to guarantee the global solution. Okay. So then we have some. This is just some standard truncation technique. So we can define the sequence of mapping Fn and the sigma n by using the truncation technique. Okay. Of course, we can easily see that these two mapping will become to be global Lipschitz. Okay. Then we can use all this sequence of global Lipschitz map to construct the approximating stochastic evolution equation. Okay. We just simply replace f by fn, sigma by sigma n, then we get this sequence of approximating SEE. Now, because this coefficient fn and sigma n, they are both globally Lipschitz, so we can see that there exists a unique global solution, multi-solution. Okay. And also, of course, the solution has continuous modification. Okay. And also, here the technique is standard one. We try to use the stopping time argument to show that the limit of the sequence of stopping now will converge to infinity almost surely, basically. Okay. So this is the way we define our solution based on the stopping time then we can use this sequence of stopping time to define a process. So basically, the xt will be equal to xnt if t is less than equal to this tn with stopping time. Okay. Of course, then this defined process xt will be defined on this set when t less than t infinity. T infinity is just the limit of this sequence of stopping time. So here the conclusion point is trying to get the prove that the t infinity basically will be equal to infinity almost surely, okay, under our assumptions. So now we can define a family of new process. So we try to apply this operate lambda I minus a to the inverse to this process xnt. We get this new one. But then because this converges to x when lambda goes to infinity, then we can get the convergency for this new process to the process xnt almost surely. Okay. So inference based on the here you see our theorem, we have this domination. Then you can easily get this convergency. Okay, this convergency. So now the idea is kind of similar to what we did in the previous part. So we try to apply the Eaton formula and to this function. So this function given the assumptions about the smoothness of this the norm. Then apply to this stopped process x and lambda t to the minimum between t and tn. Okay. Then use some basic technique. We can get the following estimate. Okay. Of course, for this example, we do not have lambda. We already get rid of lambda by let lambda go to infinity in some previous step. Okay. So finally, we can get this somehow like the moment estimate. So the good thing is on the right hand side, this is only dependent on t, but does not depend on n. Okay, so this result is enough to guarantee the this limit of the sequence of stopping now equal to infinity almost surely. Okay. So finally, we can state the result about the extension from the Lipschitz to local Lipschitz cases. So we still have the same assumption about the Banach space, satisfy the smoothness, and then the same inner product. Then now we assume that f and sigma both satisfy the local Lipschitz condition. Then we have to add this specific condition, which is essentially the same as we discussed in the previous part. Then this is the Yoshida approximation. Then under this our condition, we can also prove the similar result. Okay. So basically, this unique invariant measure for the stochastic evolution question under the local Lipschitz condition plus this specific condition. Then we also have the strong mixing property and the weak convergency, then plus this rate of convergency. Because the proof idea is kind of similar to the Lipschitz case, but we do have some extra work need to be take care. So, but it's not that difficult to do so. Okay. I think this is the end of my talk. Okay, thank you for your attention.
Other questions?
Please.
Please, can you give an example of this Banach space with property M2 other than in P spaces?
I'm not sure. I think maybe Bridget is more like expert in this situation. Yeah. I guess there, of course, there have some other Banach space. They satisfy the it's M2 Banach space.
SP space with large P.
I understand.
Yeah.
But how it is related to the usual type 2 spaces?
Not the same. The type 2 plus UMT implies M type 2.
Yes, yes, the included.
No, the
Oh, okay, what's
M type 2 is subspace of type 2.
Would sublab spaces be?
No, I mean the sublab spaces which are based on LP space with P larger equal to 2 are also matrix in type 2. So there are some abstract spaces, but from the point of view of applications, if you look.
Maybe some base or orderly spaces.
Now that I said, all the sublab spaces based on LP spaces with P larger equal to 2, all the real and complete interpolation spaces are mapping in type 2, provided the base space is M type 2.
What about smoothness of the mode? Where does that fit in?
So there is a condition which I don't remember exactly, maybe Hongwei remembers that this mapping in type 2 is equivalent to the fact that there exists equivalent norm on the Banach space which is too smooth.
Yeah. The equivalent is basically, yeah.
So this, yeah.
Yeah, I have a simple elementary question. When you construct the invariant measure, it seems to me that you actually get a stationary solution. Did I read that correctly? As opposed to just
Yeah, I think so. Yeah.
on some fancy street, but actually a strong stationary solution of the equation.
Basically, yeah. Because when you see that at the end we have this rate convergence, which is exponentially convergence, basically.
But I meant the invariant measure, because your invariant measure comes from a random variable in the Banach space. Yeah. Your invariant measure is the distribution of a random variable with values in the Banach space.
Yeah, which is the law of some not variable.
Right, it's a law.
Yeah, the law of some.
But is it actually, if you start at that random variable, do you get a stationary solution of the equation?
Yeah, I think so.
Okay, that's what I was thinking.
Yeah, I think so. Yeah, we have this the exponential rate convergence. Yeah. If you start with this measure, you end up also with this measure.
in fact, I would like to make a small comment to this talk. Maybe I would like to mention there was quite impressive, number of people who was dealing with these topics, but unfortunately there wasn't mentioned one name of a person who perhaps was one of the first doing in this things, and it's the name of Yuri Daletsky, who was one of the pioneers in the development of the, Hilbert and Banach space stochastic differential equation theory as itself. And there are a lot of results concerning type 2 Banach spaces and theory of stochastic differential equations in these spaces. So one can see it in the book by Daletsky and Fomin, which is, and in many papers of his and his students.
Okay, thank you.
Like to mention.
Yeah. So based in the book by Daletsky and you?
No,
I think it's
no,
maybe it's I don't remember the name. It's
because there was manifolds and okay. We will discuss.
But yeah, I don't remember they work on this M type 2 Banach space or not. I don't know exactly. Maybe they have some result on some Banach space, but not necessarily M type 2 Banach space.
Type 2 Banach space, we were interested there. Okay.
Okay, thank you. Yeah, we'll try to search all this literature from Professor Daletsky to find out some.
Somewhat easily.
You shouldn't forget such a name.
That's some more questions.
Did you think about attractors for this?
Attractors.
Existence of attractors?
Oh, the existence of structure? Not yet. Not yet. That will be interesting to consider, I think.
I have a simple-minded question. Suppose that you gave some example in one dimension, and you said that A was some kind of generalization of the Laplace operator. I mean, second
The second order, like an ordinary differential operator.
Okay. Now, suppose that A is Laplace operator. Can you afford getting sigma which would not be constant? Because in your example, sigma was constant.
And that was
Oh, okay, okay. So if like Professor
Yeah,
Bishop is asking me
non-constant signals as
to
well.
try to construct some example which is not constant diffusion coefficient, I will not consider this part too much. I guess we can find some example which is non-constant.
No, but you can consider Laplace operator. The emphasis here is that your semigroup is only strongly continuous without any smoothing property. So, in a sense, all the so when you have this analytic semigroup, things can become easier.
Oh,
And that will, so the whole point here is that you have a semigroup which is purely only strongly continuous without any smoothing property.
oh yeah, I see. So if you have some further like analytic property, it will be easier to construct the non-constant diffusion coefficient in this case, I think.
And it's also, these equations are PDEs as opposite to ordinary differential equations. So one should not get confused.
And you mentioned an example in LP spaces, and as we discussed at the beginning of this discussion, as we mentioned at the beginning of this discussion, sublet spaces based on LP for large P would satisfy apparently many of these properties. Can you also get examples in this kind of space?
I think so, but we have to like work more deeply there. So I think like Professor Bridger, he somehow is expert in all this subgraph space. Should know that how to find some example.
Okay. Well, if there are no other questions, let's thank the speaker again.